we left off last time talking about some implementation issues around multi-threading. So a little bit of background on what we're doing today is we're going to be finishing up multi-threading. We're going to be using cutlery. And you'll see why we're using cutlery in a minute. That's right. Whole box of forks. And we'll be talking about synchronization and synchronization primitives. So let's go back to multi-threading and look at actual simultaneous multi-threading, which is where we left off. So just to recap, we talked about different types of multi-threading. We talked about not multi-threaded processors, so you have your superscalar. We're trying to fill in the empty slots here. So we can do some fine grain, but not simultaneous multi-threading. We can do coarse grain multi-threading. You can even possibly think about trying to do this in like some fast software layer. You could think about just cutting your processor in half and using half your ALUs for one thread and half your ALUs for another thread. That is sort of technically a version of multi-threading. It's just not executing, well, it is executing at the same time, but it's not necessarily using all the resources. And then you can think about actual simultaneous multi-threading where you're issuing instructions from different threads into different functional units at the same time. So we talked about this last time, and one of the things that came up was how do you go about getting at parallelism? So if you have thread-level parallelism, you can mix and match different instruction slots from different threads and get parallelism that way. And one of the great things about actual simultaneous multi-threading is that if you have a fast superscalar machine and you try to use actual simultaneous multi-threading, you could think about trying to reduce the number of threads if you don't have enough thread-level parallelism and actually go at instruction-level parallelism. So here we see this blue cross-hatched blocks here, or instructions. And this is the same thread running in the same sort of time period. And if you have lots of threads running, you could actually intermix the different threads and run the blue cross-hatched threads slower than if you were to try to use parallel resources to run one thread faster. And this is one of the big insights here that symmetric multi-threading lets us go after. So we briefly talked and flew through this at the end of lecture last time, as we talked about what is the cost of implementing symmetric multi-threading. So conveniently, there's actually a really good example of this. The Power 4 by IBM and the Power 5 by IBM. They're very similar architectures, except the Power 5 has two-way simultaneous multi-threading, and the Power 4 is almost the same architecture without two-way symmetric multi-threading. So you look at these two pictures, one of the big things that they added is they added more fetch bandwidth, so you can fetch from two different program counters at the same time. You can decode more instructions. And then they added an extra pipe stage in here, which they do what they call group formation, which is basically the scheduling of the two different threads instructions together by the time that it reaches the execution units. Also over here, as we've talked about before, even without symmetric multi-threading, it's pretty useful to have more registers, or more physical registers, and more architectural registers. You're minimally going to need more architectural registers. More physical registers probably is a good performance thing. So we're talking about implementation details. So one of the questions that comes up is, what is the cost of actually going to implement this symmetric multi-threading on this processor? And one of the questions that also comes up here is, why 2 threads instead of 4 threads, or 8 threads, or more threads? It has cost. So that's one of the things, is that they would actually have to start replicating more data structures. For the pipeline that they had roughly left over from the Power 4, they had enough compute and bandwidth through their execution units to be able to handle 2 threads. But if they wanted to try to go to more threads, they basically would bottleneck somewhere in their architectures. I don't completely know exactly where they bottlenecked, but the paper talks about this, basically says that they bottleneck somewhere in their execution units. They kind of leave it a little vague. So they decided that it wasn't worth adding more in 2 threads because it's not going to give you any performance increase unless you have threads that don't have or threads that have a lot of stalls. If you have threads with enough stalls, you could probably have enough holes to try to intermix another thread in there. So some of the changes in the hardware they went about doing, well, they actually increased their cache size. They increased the associativity of their caches. Their last level cache here, they went to 1.92 megabytes versus 1.44 of their L2 and their L3 together, sorry. And you can see here, one of the interesting things is they start to actually separate data structures. Because if you have multiple threads running and you try to mix them all into one big data structure, one of the problems that, or one big hardware data structure, one of the problems that comes up is maybe one of the threads is going to hog the data structure. So threading actually introduces a lot of complexity having to do with figuring out how to be fair in the usage of the structures. So one solution is you just replicate. So anywhere it was hard to get it right or hard to have, they had a lot of conflicts, you could just replicate. So they added a separate instruction fetch, prefetch, and buffering. And then they added more, they call them virtual registers here, but it's more physical registers effectively, so more places to schedule into. So there was some added hardware cost to this. And to give you an idea of sort of area, 24% area improvement, increase. A lot of this is just due to the cache, because they made their cache so much larger. So you have to ask yourself, does it make sense to use that 24% more area to run 2 threads, or at what point does it make sense just to plop down a second processor? It's a tough trade there. Well, if it's 24% bigger and you get a 2x performance boost, it was a good trade. If it's 24% bigger and you get less than a 24% performance boost, it's pretty questionable. So let's look at another example, and then we'll wrap up with the performance of this and see if they did get their 24% performance boost. The first implementation of symmetric multi-threading, there's been many implementations of multi-threading, but excuse me, not symmetric, simultaneous multi-threading was the Pentium 4 processor. Now, they called it hyper-threading. That's a Intel marketing term. It is simultaneous multi-threading. But the Pentium 4, they didn't actually replicate very many structures. And they didn't really change the processor very much. In fact, there's basically modes to turn off simultaneous multi-threading in the Pentium 4. And it was not a flagship feature when the processor was first shipped. So the basic idea in the Pentium 4, the little bit of extra hardware they added was they did duplicate some resources here. So overall, they increased their die area by about 5%. So it was a very, very small amount. Now the question is, what is the performance boost they could get from this? And one of the interesting things here is that there was a big problem that started to come up with the Pentium 4 that when you were trying to run one thread on it, well, you weren't guaranteed that the performance of that one thread would be equal to if you turned off hyper-threading, or sorry, simultaneous multi-threading. So they had a mode switch. They could turn off where they would take some structures that they would partition when they were in multi-threading mode and partition them 50-50. So you didn't have deadlock problems, and they didn't have resource contention problems on these shared structures. And when you turn this mode switch off, some programs got faster. To some extent, what that meant is they didn't size those structures correctly to be running in multi-threading mode at all times. And the switch was not like a little switch. It was like a big switch. You had to reboot your computer to change the switch. It was a boot time parameter to the chip. And this left such a bad taste in Intel's mouth that simultaneous multi-threading got kicked out of Intel land for a few generations. The Pentium M, Core Duo, Core 2 Duo, all kicked out simultaneous multi-threading. And it didn't work its way back in until Nehalem, Core i5, i7 sort of processors very recently. So it's interesting to see that you can use a little bit of hardware, but you have to be careful. Now, what was the biggest problem that they had here? The biggest problem was that the load store queue on the Pentium 4 was split in half when they were running in 2-thread mode. So the first Pentium 4 architecture that was shipped, it had symmetric or simultaneous multithreading turned on. They just split the structure in half. And it didn't have enough bandwidth for lots of programs, or didn't have enough entries in there for lots of programs when it was cut in half. So it was sized to run 1 thread. They cut it in half statically, and when they tried to run 2 threads, it was effectively not providing enough performance. So they couldn't get enough loads out to the memory system from 1 thread when they cut that structure in half. So it really starts to bring up the question of what is the right allocation of resources, and should you use some sort of round-robin scheme? Should you use dynamic allocation? Should you use static allocation? Should you replicate? If you replicate, it costs more area. And these are some of the big challenges here. OK, so let's look at some of the performance here. So the numbers were pretty abysmal for the Pentium 4, even when everything was going well. So example here, Pentium 4, Extreme Edition with simultaneous multithreading, give you 1% speed up when you're running 2 threads for spec-int rate. So you're running multiple copies of the same program. That's how spec rate is done. That was the integer one. For the floating point one, it did a little bit better, a 7% improvement. Now, that's not horrible, considering it was only a 5% area improvement, or area increase. But still, that's not saying a whole lot. I mean, you have to question if this whole level of complexity was worth it. And was that 5% area, could have been used for something else to get a few percent performance increase? And this was, to some extent, pretty typical across applications for the Pentium 4. One of the interesting things about the Pentium 4 was, because the cache wasn't huge, especially the L1 cache was relatively small because they wanted it to operate so fast at their very high clock frequencies, you could get a lot of data pollution in there from the 2 threads, and they would actually destructively interfere in your level 1 cache. So that was one of the big things they had to try to make up was, this is a problem with any multi-threading, not just simultaneous multi-threading, is you can actually fight for space in the cache and end up with both capacity and conflict misses. The Power 5 did a lot better here. You know, it was, they thought a little bit harder about sharing structures, duplicating structures, and allocation of different resources in there. So on spec-int rates, they were getting 23% improvement for their 25% area. OK, well, this might actually be a good idea. It might have some value. And for the floating point version, they were not doing great, but doing better here. And the floating point apps had a lot of cache conflicts. So the floating point spec FP apps, if you go look at them on the inside, they typically have very large data sets. So they were basically conflicting in their larger last level caches and things like that. So finally, I wanted to just give a little bit of color to this idea of picking fairly and not having starvation in different resources in a simultaneous multi-threading pipeline. So one processor that's sort of the famous simultaneous multi-threading processor that was never built was the EV8, or the Digital Equipment Corporation last alpha that was never built. So this last alpha, the EV8, or also known as the 21464, had introduced, they had 8-way threaded processors. Note, this was never built, but it was a out-of-order superscalar that had 8-way simultaneous multi-threading. It also was a very aggressive processor. And when I say it was never built, it was never shipped commercially. They went pretty far in the design of it. So one of the questions that they realized upon here is, what is the right way in an out-of-order pipeline to make sure that you're getting correct utilization of the pipeline when you're issuing instructions from different threads. So in this example here, we have 4 different threads, we'll say. And you need to choose to go into your multi-issue out-of-order pipeline here which thread to go pick from. And by definition, you want to try to fill in the holes of one of the threads with work from another thread. So complete fairness here, or lockstep round-robin choosing, for instance, is not what you want to do. Completely the wrong thing to do, because you want to fill in when one processor is stalled with other processors' work. But you want to make sure that the thread, which let's say has no dependencies on each other, or could run very fast, doesn't go to memory very often, we'll say, just doesn't stall very often, doesn't just hog the processor. Because it's never going to introduce stall cycles on itself, by itself. So they came up with this idea called iCount. And it was a choosing policy which basically looked at the number of instructions that were retiring out of the back of the pipeline, had like a moving window to try to estimate how many instructions from each thread we're completing, and then feedback around to the front of the pipeline here to determine where to issue from. So I was just wanting to get across the idea that if you try to intermix different threads in a data structure, it's relatively simple. You can either cut the data structure in half or have some round-robin allocation there. It gets much more complicated when you have a full processor pipeline that you need to figure out how to issue into that processor pipeline, and then 20 stages later, something happens. There's so much stuff in flight that you need to worry about this a little bit harder. So here, they basically were looking at how many instructions were in flight and how many instructions had recently committed from a thread to determine what to do. And on average, they were hoping that they had some fairness between the threads.